విధానంలో డాక్టర్ బిఆర్ అంబేద్కర్ ఓపెన్ యూనివర్సిటీ దేశంలోనే మొట్టమొదటి సార్వత్రిక విశ్వవిద్యాలయం. దాదాపు 2.5 దశాబ్దాలుగా దూర విద్యా విధానం ద్వారా కంప్యూటర్ కోర్సును అనుసంధానం చేస్తూ BA, BCom, BSc డిగ్రీ కోర్సులను అందిస్తోంది. పోస్ట్ గ్రాడ్యుయేషన్ స్థాయి, డిగ్రీ, డిప్లొమా స్థాయి కోర్సులను ఔత్సాహికులైన విద్యార్థులకు అందిస్తోంది. డాక్టర్ బిఆర్ అంబేద్కర్ సార్వత్రిక విశ్వవిద్యాలయం స్థానికంగా స్వయం బోధనా పద్ధతిలో ముద్రణ రూపంలో రూపొందించిన కోర్స్ మెటీరియల్ అందిస్తోంది. కోర్స్ మెటీరియల్ అధ్యయనానికి సహకరించే విధంగా రేడియో, టెలివిజన్ పాఠ్యాంశాల ఆధారంగా కార్యక్రమాలు ప్రసారం చేస్తోంది. అధ్యయన కేంద్రాల ద్వారా ఏర్పాటు చేసే సలహా సంసర్గ తరగతులు, సైన్స్ ప్రాక్టికల్ సౌకర్యాలు విద్యార్థులకు స్వయం అధ్యయనానికి ఒక చక్కటి అవకాశం. ఇవి విద్యార్థి సమీపంలో ఉండే అధ్యయన కేంద్రం నుంచే పొందొచ్చు.
Dear students of Dr. B.R. Ambedkar Open University, viewers, DD Yadagiri, Namaskar. Dr. B.R. Ambedkar Open University, Department of Chemistry, producing a video conference live program on synthetic strategies. This topic is taken from the paper 6, M.Sc second year, and also introductory part covered in the BSc final year, 6th semester core course. This topic, for explaining this topic, we have eminent personalities here. They are J. Mohanbabu from Nizam College, Usmania University, and Areef Mohammad, Usmania University, and JE faculty also. And this program is of 60 minutes. In first 50 minutes, we are going to cover the topic details, and we will explain in this 15 minutes. Later, you can call to the studio. You will ask your doubts to the following phone numbers: 040-27031-1431, 040-2703-1432, 2703-1433. Now coming to the topic title is synthetic strategies. We can define it in single line, that is planning a synthesis of a molecule. That is a single line definition. Now, why we need to synthesize these molecules? The synthesis is required for the several aspects and several requirements. We are taking the criteria, 5 criteria we can take to synthesize a molecules. We know that the chemist is working on the synthesis of molecule. He required various needs to fulfill the his requirements. You need to synthesize various molecules. The criteria for the synthesizing molecules are: the first one is structural verification. Structural verification means several molecules or several compounds we are isolated from the natural products like plants, animals, marines, and soil also. All these compounds are, most of them are unknown compounds. That means novel compounds. For the novel compounds, we need to determine the structure, that is structure elucidation part. This structure elucidation part includes several reactions, some degradation reactions. After all these steps, we are confirming the structure, but the confirmation is fulfilled by the synthesis. We need to synthesize it. After then, we need to confirm. Then for the synthesis, it involves the several steps. Therefore, we need to plan the synthesis of those molecules. The planning is involving in such a way that it is easy in process and easy to handle and also cost effective. In the similar way, the second category is biological activity. Most of the organic molecules are drugs, medicines, and fertilizers, insecticides. Several uses are there. For that purpose, we are going to invent the new molecules and synthesize the new molecules and confirm their structure, and also we need to scale up to commercial use. For that purpose, we need to synthesize it. For the biological activity also, we need to do several investigations in the for approving the drugs and medicines. Therefore, the molecules we are going to synthesize, those are used for the drugs and medicine. We need to identify their biological compounds, biological activities, and also we need to confirm their synthesis by simple methods and cost effective methods. And the third one is analog studies. We are isolated the natural products from the plants and animals, etc. Those compounds we are going to identify they have some biological activity, but they have some side effects, and also they require large excess, and we need to modify also side effects also there, and a lower potency. All these things are generally observed in the naturally isolated compounds. Then we need to improve the structures. For the improvement, we need to synthesize their analogs. For example, quinine is there. Quinine is reported as anti-malarial. After quinine, we are synthesized several molecules, several molecules of anti-malarials. These are all taken from the nilidinic acid and quinine, in such a way that analogs are very important molecules. We need to improve the potency and decrease the side effects and also cost effective. And the third one is topological challenges. Topological challenges means some artwork is happening in the chemistry. Artwork means we know that fullerenes, cumines, and icosahydrals, dodecahydrals, like large sized compounds are there. They have the several importances there in the nanotechnology and the drug delivery system. All these things are involving these bulkier molecules. Therefore, we need to synthesize them. For the synthesis of these large molecules requires large effect and very hard effect. Hard efforts are required. Therefore, we need to plan the synthesis of these all these molecules. And last one is inventing or reporting the novel reactions and novel reagents, and investigation of the mechanisms. Several reactions are there till now we are already known, but their mechanisms are not well studied. In this reason, we are going to synthesize some molecule. Those molecules are confounds the mechanism pathways of that particular reactions. Similarly, we are going to identify new or novel reactions as well as new reagents which are used for the facilitating easy synthesis of several compounds. Okay, in this, based on these 5 criteria, we are going to plan the synthesis of several organic compounds. This plan depends on the thoroughly knowledge in the synthetic strategies. All these things depends on the synthetic strategies. Synthetic strategies are also called disconnection approach. Okay, to explain this topic, I am asking the first question, Mr. Mohanbabu garu, please explain what is the disconnection approach and what are the terminology we are encountered in the study of the synthetic strategies.
Yeah. So, sorry. So actually here the disconnection approach means generally the basically how to define the disconnection approach or the synthetic strategies means. So simply you can say the disconnection approach, it is a planning to the synthesis, right. So while you are doing the synthesis, right, so we will face so many problems here, means we don't have the sufficient reagents, we don't have the sufficient reaction pathway, and we don't have the sufficient other suitable, okay, the suitable substrate here, right. So for that purpose we need to plan a synthetic pathway in a proper way. So in this purpose we need to take a criteria here, right. So here that particular criteria will be studied in this particular disconnection approach here. So basically we are come across about the 2 types of means synthetic methods here. So in one type of synthetic method where the starting material or the substrate will be provided and the product will be provided, means we will know the structure of the substrate as well as the product here, right. So only thing is the chemist who is attempting the synthesis here, so he may plan the reaction pathway and he may means provide the sufficient reagents for the conversion of the particular substrate into the product. That is one type of synthesis here, means where the reactant and products both will be known structure here. Okay, that is one type of reactions means method here. So generally we call this is the forward synthesis reaction. That is very common reaction which takes place in the laboratories and in the industries here. And the second type of synthesis is a retrosynthesis, right. So in this retrosynthesis, we know the structure of the target molecule here, means we know the structure of the product, but we don't know the structure of the reactants here. So the chemist must identify the reactants from the product here, right. So generally in the synthetic strategy, we call this product as a target molecule here, right. So by taking the target molecule, so we will make down the means we will break down the appropriate bonds here, we call that is a strategic bonds, okay, and by following some guidelines which are provided in this particular topic here, right. By following these guidelines, we will break down particular strategic bond, and we will find out the final simple and commercially available material that called as the synthon, or sometimes it is called the precursor here, right. So what you do is here, by taking the target molecule, we will identify the precursor molecule here, right. So by taking that precursor molecule, again we will build up that structure of the target molecule, right. So that is second type of synthesis here, right. So these are the two types of synthesis which are having in the organic chemistry, okay. But while you are doing the synthesis, while you are doing the disconnection here, so many terminologies are involved. So many terminologies are involved, like what is that target molecule, functionalization, functional group interconversion, disconnection, synthon, synthetic equivalent, transform, and retron. So these 8 type of terminologies will be encounter in this particular synthetic strategies or the disconnection approach here, right. And each and every terminology will have its own importance here, okay. So each and every terminology will have its own importance, and these type of all these terminologies having some definition. So we will see the definitions of all these terminologies here, and we will see the examples for each and every terminology here. So first if we take the target molecule here. So the target molecule nothing but the molecule which is to be synthesized in the synthetic project here, right. So the target molecule which is going to be synthesized in the synthetic project here, that is target molecule. Next, functionalization. So when you are doing the when you are attempting the synthesis here, so we will face some functionalization, means we need to introduce some functional groups in the substrate molecule, right. So the functionalization means where the introduction of the functional group into the substrate molecule is called the functionalization. Like we have so many functionalization like acylation, bromination, formylation, nitration, and chlorination, all these are the functionalizations. So what we are trying to attempt means we are trying to introducing a functional group in that particular substrate molecule. So that is called the functionalization. Next, functional group interconversion. So in this functional group interconversion means here while we are doing the synthesis, means while we are building the synthesis for a particular target molecule, okay. So some compounds, right, some compounds will not be facilitates for the introducing the functional group directly, right. So in that case we will introduce particular functional group in indirect manner here, right. So this is called the functional group interconversion, means simply you can say where the conversion of the one functional group into another functional group is called the functional group interconversion, right. So for example, in this particular example you can see where the toluene is taken and we are trying to introduce the amino group on the toluene here, right. But the amino group directly cannot be introduced on the toluene molecule because it is not convenient for the introduction on the toluene here. That's why we will introduce the amino group on the toluene molecule by following the doing some other conversion here, right. Interconversion means where we will do the nitration to the toluene, then we will get the nitro substitution product here. After that we will do the reduction to this particular nitrotoluene here, okay. So then we will get the toluidine, right. So toluidine product here, or you can say it is amino toluene compound, yeah, paratoluidine. So in this way this particular toluidine is introduced by via nitro compound here, right. So indirectly we are introducing that particular amino group on the toluene here. So this type of conversion is called the functional group interconversion. And the next type of terminology which is encounter in this particular synthetic strategies is synthon here, right. So what is meant by synthon here, right. So synthons nothing but these are the idealized fragment molecules which are happened during this disconnection approach here, right. So when we are doing the disconnection operation, okay, so means what we do in the disconnection here, so we will break down the imaginary, we will break down the bonds here, strategic bond, okay, the appropriate bond will be undergoes cleavage in this particular operation here. So during this cleavage we will get some small fragments, okay, those fragments are called as synthons here. For example, in this example you can see where the aryl alkyl ketone compound, where the particular the bond which is attached to the benzene ring, it is undergoing to cleavage and it is disconnection. Cleavage means disconnection. So then it is resulting from the formation of the two fragments here. One is the alkyl substituted benzene and another is a acyl alkyl acyl group here, right. And here the two possibilities are there, means where generally here the synthons usually they are having the charged species here, means they carry say either negative charge or the positive charge here, okay. So here the keeping the charges positive and negative charges here, there are two possibilities, right, where the aromatic ring it may carry a positive charge or the negative charge, and the acyl group it may carry a positive charge or the negative charge here, means so this is the possibility after doing the disconnection to this particular target molecule here, right. So this is called the synthon here, where are the small fragments which are resulting from the disconnection approach. And the next terminology which is comes in this particular disconnection approach is the synthetic equivalent here, right. So generally the synthons, right, usually the synthons are not stable species here, because they are carrying the charges, so directly they cannot be used in the forward synthesis reaction here. So they may convert into the stable compound, right, those are called as the synthetic equivalents, right. So means here the definition is the synthetic equivalent is the compound or a mixture of compounds which is used in place of synthon, okay. For example, here in this particular example you are given where the acetyl chloride and aluminum chloride collectively known as the synthetic equivalent for the acyl carbocation here, right. So means in place of acyl carbocation you can use the acetyl chloride and aluminum chloride here, okay. And sulfuric acid, concentrated sulfuric acid and concentrated nitric acid, generally we call it is as a nitrating mixture, right. So this nitrating mixture is the synthetic equivalent for the nitronium ion here, NO2 plus, right. And for formyl cation here we can use a formylating agent like POCl3 or whatever, right. And for the carboxylate ion we can use the cyanide group or the carbon dioxide as a synthetic equivalent. And if any halide group is there, halide synthon is present, so you can use as a halogen molecule as a synthetic equivalent for that one. And where the secondary alcohol is present, right. So if the alcohol group is present adjacent to the carbocation, right, so that will be converted into means carbonyl group, and it is used as a synthetic equivalent. So you can see the different types of synthetic equivalents for the different types of synthons in this particular table here. So this is synthetic equivalent. Next, the disconnection. So generally in the retrosynthesis, right, retro means reverse actually, the meaning of retro means reverse. So in the retrosynthesis, so we will attempt to disconnect a strategic bond in order to get the starting material or the precursor here, right. So this particular bond will be undergoes a disconnection, and for this disconnection, right, so we can follow some guidelines here, means that bond when you attempting the forward synthesis, that bond must be easily formed again in the forward synthesis reaction, right. So that particular operation is called the disconnection, where the cleavage of the bond or the disconnection of the bond is called the disconnection. Next type of terminology which is used in this particular retrosynthesis is the transform. So generally here, according to Corey, scientist here, he proposed the name of the transform here, right? So it is exactly reverse to the synthetic reaction here, right? Where the in the synthetic reaction, what happens here, where the reactant converts into product, but in the transform, so what you say, what you do is here, by taking the target molecule, so we will find out the reactant here, right? So here the transform is, it is a special name which is used in the synthetic strategies or the retrosynthesis here. So here when you see the target molecule, so you will visualize the particular reactants or the precursors by seeing the structure here, right? So that is called the transform here, right? So transform means we will convert that particular target molecule into the feasible reactants or the precursors here, okay? So here different types of transforms are available by, means we will get different types of transforms by doing some kind of operations here. So here means the transform which will be done by the cleavage of the rings here, right? So in this particular tetralone, right? So in this particular tetralone, where you can cleave the, you can means break that particular bond which is attached to the benzene ring, then it leads to formation of a that particular benzoic acid here, right? And here the transform, it is denoted with the special arrow mark, means double arrow mark here, okay? So when you re-attempt the synthesis of this particular tetralone, right, that reaction must be easily formed here, and the reagents must be available, commercially available, and they must not cost effective here, okay? So this kind of means precaution you should take while you are doing the transform here, okay? And next you can see do the transform by removing these stereogenic centers here, right? So where you can see the epoxide ring is there, right? So when you do the operation of the disconnection, so you will get the methyl cyclohexene is the transform to this particular epoxide here. So when you do when you react this particular methyl cyclohexene with what is means perbenzoic acid, means MCPBA, or any sharpless epoxidation reagent, so you will get that particular epoxide ring here. And where in the second example you can see that diols is there, and it is transformed into the what is that cyclohexene here, right? So when you add the osmium tetroxide or Woodward oxidation reaction, again you will get the cis diol product here. So in this way, that transformation should be easily convertible, okay? So that is the transform. Next, the retron, the next terminology which is comes in this particular retrosynthesis is the retron. So what is meant by retron is the minimal structural element that should be present in a target molecule, okay? So means here when you see the structure of particular target molecule, okay, so that means the means substrate molecule, means or the precursor structure must be present in that particular starting material. So that called the retron here, right? So various examples are given for the retron. You can see in the cyclohexene, right? So for this cyclohexene retron, you can take butadiene and what is that ethylene as a precursor for this cyclohexene. So when you do the 2,4, right, 2 plus 4 cycloaddition reaction, again you will get the cyclohexene product here, Diels-Alder reaction, right? Simply called it is a Diels-Alder reaction, and very easy reaction and very famous reaction here, right? Means here when you are attempting the this disconnection, you must visualize that the reaction is easily carried out, okay? So here in the particular next example you can see where the 2-phenyl indole, right? In the 2-phenyl indole, so where this 2-phenyl indole will be obtained by doing the Fischer-Indole synthesis. So for that we can visualize that the reactants, the estophenone and phenylhydrazine, right? Phenylhydrazine and estophenones are the precursor for this particular 2-phenyl indole what is that retron here. So in this way you can build a particular synthetic pathway for the different type of reactions here, and you can see the different type of target molecule and their transform and retron and precursors here. So it is prescribed in this type of, this is in the table here. So you can see where beta hydroxy is ester is there. Okay, so you can take the transform as this particular aldol, okay, and enolate ion as a transform here, and precursors we usually when you break down the middle bond here, so generally the phenyl benzaldehyde and the ester is a what is that precursor for this particular target molecule here, right. So in this way these are the different types of terminologies which are involved in this retrosynthetic analysis.
Now I ask you second question, Mr. Areef Mohammad. Please explain the strategies involved in the synthesis of various aromatic compounds and what are the required guidelines for synthesis of them.
Yeah. So, well, if you want to do the retrosynthesis, first of all you should know two things. Number one is disconnections, another one is functional group interconversions. So actually these disconnections and functional group interconversions cannot be carried out in the laboratory. If you see any organic synthesis, we will go to the laboratory and you can synthesize, right. But this both are hypothetical things you cannot do in a laboratory, but you can do on a paper. If you are doing in a paper means you should know the what is the morphology of the target molecule particularly, right. It is an essential requirement to know the what is the exact morphology of your target molecule, then only you can do the disconnections or functional group interconversions. So this both are very vital to the retrosynthetic analysis. So in this session we are going to learn about disconnections. So first of all, what is the meaning of disconnection is, it is an imaginary bond cleavage of your target molecule, right. It can be done in a paper only, not in a laboratory. So these disconnections are very important. So how to do the disconnection is a big question. How to do the disconnection and where to do the disconnection and why we are doing a disconnection in a particular area but not in another area. So these, in order to answer these all questions, we have a certain guidelines, or you can call them a rules or anything, right. So when you have a target molecule on your paper, you should not do the disconnection randomly. You have to be abide by these rules, then only your disconnection will be fruitful and you will get your result synthesis will be, the real synthesis will be carried out very easily. So let us discuss what are these guidelines. So I will tell you 5 guidelines today and 2 tips which are useful to disconnect. If you understand them easily, if you understand them in the universe, if I given you any target molecule, you can disconnect it very easily, and those guidelines also very simple. Those all depends on your only electronical properties, right. So let us see them. So the guideline number 1 is, when you have a target molecule, if you are disconnecting, the disconnection must be known. Randomly you should not do disconnect anything. Whatever the disconnection you have done, that disconnection practically it should be possible, then only your disconnection is correct, right. And after disconnection, whatever you are getting the synthons and synthetic equivalents, they should be easily available and they should be cost effective, means they should be cheaper, then only your disconnection is fruitful. Otherwise your disconnection will be unuseful, right. So this is the guideline number 1, right. So now let us see the guideline number 2 is, now when I have given you a target molecule, you should know what are the functional groups present in the target molecule. If you know the functional group, then only you can disconnect, right. So in your target molecule, what are the functional groups are present, you should identify them, right. So first you should disconnect that functional group instead of your aromatic skeleton. Why? Because it is very difficult to prepare the aromatic skeleton, so we will not prefer to disconnect the aromatic skeleton. So simply we will disconnect the functional group. So in a target molecule, find out the functional group and disconnect the functional group, but don't disturb the aromatic ring. This is guideline number 2, right. So now guideline number 3 is, in your target molecule, find the heteroatoms, where the heteroatoms are present. Why? Because in real synthesis, the bonds between heteroatom and carbon, they will form very easily, right. So because of that, you find the heteroatoms and cleave the bonds, or you disconnect the bonds which are directly attached to the heteroatoms. This is guideline number 3, right. Now let us see the guideline number 4. Now you have found the heteroatom, but unfortunately what happened is these heteroatom directly connected to the aromatic ring. You should not disconnect, you should not prefer to disconnect such bonds. You try to avoid them. Why? Because if you disconnect the bond between heteroatom and aromatic ring, what is the synthons you will get? Oxygen will get the negative charge and aromatic ring will get the positive charge. So as we know that aromaticity will be disturbed if positive charge is accumulated on your benzene ring. So your synthon will become unstable. So you try to avoid them. I am not telling you that you should not disconnect them. You should try to avoid them. If you don't have any chance, then you may disconnect. That disconnection may be allowed, right? So I am not restricting you that don't disconnect it. You can disconnect, but when there is no other option, then only you can disconnect. This is guideline number 3. Now 4. Now let us see last guideline, which is very important, is in your target molecule you have a many functional groups. If you have a one functional group, doesn't matter, you will go there and you will disconnect it. But unfortunately what happened, in your target molecule there are more than one functional groups are present, like acid is present, sulfonic acid is present, aldehyde, like different functional groups, functionalities are there in your target molecule. In such cases a question will be arises, which functional group I should disconnect first, right? So in such cases what we will do is, we will do the chemoselective disconnection. First let us see what is the meaning of chemoselectivity. So in your target molecule you have a more than one functional group. In such cases what we will do is, we will disconnect selectively only one functional group among all other functional groups. That disconnection is called chemoselective disconnection. Now which functional group I should disconnect is a big question. So simple, what is the tip number 1? So 5 guidelines are over. So now tip number 1, what is tip number 1 is, when different reactivity, different functional groups means they have a different reactivity, right? So if they are different reactivity, you disconnect the bond which is more reactive. You should disconnect the bond which is more reactive. Why? Because during in the retrosynthesis, the disconnection which you done at the beginning, in real synthesis it will form last. If you are doing the disconnection at the last, in real synthesis it will form very beginning. So if more reactive functional group, if you are not disconnecting at the beginning, if you are disconnecting at the last, what will happen in real synthesis? It will form first. In real synthesis, if more reactive functional group is formed, then what will happen? This more reactive functional group will react with other reagents, then you may get undesirable products, right? So to avoid this problem, what we will do, we will not disconnect, we have to disconnect the more reactive functional group first, rather low reactive functional group. This is tip number 1. Now tip number 2 is, in your target molecule, if you have a electron withdrawing groups and electron donating groups, you prefer to disconnect the electron withdrawing group first, right? Why? I will tell you with example. For example, in your target molecule you have electron withdrawing groups and electron donating groups. In such cases you prefer to disconnect the strong electron withdrawing group first, after that moderate electron withdrawing group, after that moderate activating group, after that strong activating groups. So these are the 5 guidelines and 2 tips, right? So by using them we will disconnect and we will see everything, right? So let us see in the slide. If you see in the slide, see one example is given. In that example, benzene is consist of methyl group and tertiary butyl group, NO2 groups, and 2 NO2 groups are present. If you see in the pathway 2, I have disconnected what? Tertiary butyl group I have disconnected. If you disconnect the tertiary butyl group, what is the synthon you got? Trinitrotoluene you got. So see, this is transformation. When you do the transformation, you should imagine the real reaction also. In real, if you want to get back your target molecule, what you should do? This dinitrotoluene should react with a tertiary butyl chloride in presence of AlCl3. That is Friedel-Crafts alkylation I have to do. So in Friedel-Crafts alkylation, what is the intermediate I will get? I will get tertiary butyl carbocation, I will get the intermediate. Now here in toluene, 2 NO2 groups are nothing but -I groups, which are very strong -I groups. They can withdraw the electrons from the benzene ring. So a partial positive charge will be, strong positive charge will be accumulated on your benzene ring. Now how this carbocation again it will go and attack to your benzene ring? It is not possible, right? So because of that the pathway 2 is wrong. So this is the reason why I told you first you should disconnect the electron withdrawing group first. Whereas comes to in pathway 1, if you see in the pathway 1, what I have done, I have disconnected the NO2 groups first. If I disconnected the NO2 group first, what I got para-tertiary butyl toluene I got. Now imagine the reverse reaction. I want to introduce the NO2 groups, right? NO2 groups can be introduced by what? Which process? By using the nitration process we will introduce the NO2 groups, right? So in this ring one methyl group is there and tertiary butyl group is there. Methyl have a 3 alpha hydrogens and tertiary butyl have a 0 alpha hydrogen. So which is a strong activating group? Methyl is a strong activating group. So because of that, when you do the nitration, the two NO2 plus cations will be substituted with respect to methyl group, but not your tertiary butyl group. So I have imagined the real reaction. If you see in the real reaction, what happened? Our transformation proved that it is incorrect, right? So further, if you do the disconnection, now I told you that strong donating group and weak donating group is there. Which group you should disconnect first? You should disconnect the weak donating group first, right? So tertiary butyl is there, methyl is there. Which is a weak donating group? Tertiary butyl. Why? You should consider the hyperconjugation but not the inductive effect. Here what is the mistake we will do is, there are 3 methyl groups, above only one methyl group is there. So alkyl groups are plus I group. So plus I effect is more in tertiary butyl and methyl it is a less plus I. So we are in that misconception. But what happened here? You should see the hyperconjugation. Hyperconjugation dominates over inductive effect. So what will happen? Methyl have a 3 hyperconjugation structures and 3 alpha hydrogens, and your tertiary butyl have a 0 alpha hydrogens. So alpha hydrogens will be dominates. So because of that, our methyl group is a strong activating groups. You should disconnect the tertiary butyl but not the alkyl group. So you get the toluene. So this is very important when you are doing the transformation. When you are doing the transformation of the backward reaction, you should imagine the real reaction also. That is very, very important. And I told you about chemoselective disconnection. To avoid the problem, I given you the table in the slide. So there are many functional groups. For example, see, COH group is present, SO3H group is present, COO minus, COCl, CONH and CN, these all groups are present. So these all are present in one molecule. What we will do? First we should disconnect the COOH, after that we should disconnect the SO3H. You should follow that priority order, then your disconnection is viable, right? So by using these 5 guidelines, I have made one small exercise where 5 molecules are there, where to disconnect we have to decide, right? So in if you see in molecule number 1, if you see in a molecule number 1, 2 benzene rings, 2 chlorobenzenes directly attached with one oxygen atom. So I told you guideline number 3. In guideline number 3, I told that heteroatom disconnect first. But in oxygen atom, see, 2 types of disconnections are possible. One is A, another one is B. But see, A disconnection, heteroatom is directly attached to the aromatic ring. In B disconnection, heteroatom is so here in B disconnection, heteroatom and benzene ring separated with by one carbon. If you do the disconnection here in B disconnection, if you will do, what will happen? You will get a stable synthons, right? Oxygen will get the negative charge and carbon will get the positive charge. So benzyl cation and phenoxadiene, which is said to be very stable. So this is we are proving our guideline, right? So this is molecule 1. If you see in molecule 2, so there are A, B, C, D, there are 4 disconnections are there. Now selectively which disconnection you should select, let us see now. Now nitrogen is there, oxygen is there, simple, the rule number tip number 2 I told you, right? So nitrogen is there and oxygen is there, which is a more electronegativity. Oxygen have a more electronegative than compared to the nitrogen. So more the electronegative means more the withdrawing tendency. So you should disconnect at oxygen site but not nitrogen site, right? So now oxygen site, again you have a and B disconnection, right? So among A and B disconnection, this is A and this is B. Now A disconnection, the bond is directly attached with the aromatic ring. As we discussed, we should not disturb this bond. So disconnect the B disconnection first. So among these 4 disconnections, which bond we are disconnecting? We are disconnecting the bond B. This is compound 2. Now let us see the compound 3 again. So see, so here tertiary butyl is there, acyl cation is there, So simply our guideline, we know electron withdrawing group, donating group, which one we should disconnect? We should disconnect the electron withdrawing group, that is A but not B, right? If you see in compound 4, in compound 4 what happened? Between oxygen benzyl carbon, one A is there, and oxygen and alkyl carbon B is there. See, imagine the synthons. Imagine the synthons. Whenever you will get this type of conflicts, imagine the synthons. What are those synthons? Is oxygen and carbon have a benzyl cation. Carbon have a benzyl cation. Carbon have a benzyl cation. So A disconnection. Whereas comes to B, you are getting a primary carbocation. In A, you are getting a benzyl cation, right? So which is more stable? A, benzyl cation is more stable, so you should prefer the A disconnection but not the B disconnection. So if you see the compound number 5, also same, electron donating group is there, electron withdrawing group is there. Which disconnection you should prefer? Electron withdrawing group, that is B disconnection you should do, after that A disconnection. Let us see some more examples which are given in your text, right? So this is one best example, that is benzocaine we are taking. So first do the transformation. So where the heteroatom is present, oxygen heteroatom, which is more electronegative. So you should do the disconnection between oxygen and carbon. Then what you will get? You will get a para amino benzoic acid you will get. Again do the reduction, you will get the acid and NO2. See here, NH2 is a one of the best functional group which we will use. So NH2 can be transformed into NO2, and again NO2 also can be transformed into NH2. Again in NH2, by doing the diazotization and H3PO2 we can remove it. So NH2 is a best dummy group. So how does it will be useful to our transformation also we will discuss, right? So you will get the NO2. After that do the oxidation. So which oxidation you will do? See, acid is changes into CH3 group. If you will use the hot-end alkaline KMNO4, it is the best reduction which will convert the benzyl. If you have at least one CH benzylic hydrogen, if it is maybe isopropyl group or any group, if at least one CH benzylic carbon is there, the total group will changes into carboxylic acid. So you do the permanganate oxidation, you will get the methyl. And how to know after that? More electronegative is NO2. So disconnect the NO2. So these are FGIs. What happened here? Acid is changes into CH3, the functional group is changed. This is called FGI, right? So now NO2 and methyl group is there. Which one you should disconnect first? NO2 you should disconnect first. What is the reason? Because NO2 is a strong electron withdrawing group, CH3 is a electron donating group. So disconnect the NO2, you will get the toluene. Further, if you want to do, again disconnect the methyl group, you will get the benzene plus Friedel-Crafts alkylation. Benzene also again you can disconnect into acetylene. Upon red hot copper tubes, again you will get back your benzene, right? So this is the original synthetic method which is given. So methyl, toluene is there. Toluene, what you will do? Just simply do the nitration. If you will do the nitration, what will happen? You will get the para-nitrotoluene. Again para-nitrotoluene. If you will use the KMNO4, alkaline KMNO4, it have a benzylic CH hydrogen. So because of that, the total methyl group, it will changes into the acid group. After that, do the palladium C in presence of H2, or else any metallic acid medium reduction like tin HCl, palladium HCl, acid mediated metallic reduction you do, then what will happen is NO2 will changes into NH2. And after that, see, we are using ethanol in presence of H plus. It is an example of esterification reaction. Acid plus alcohol, always we will result a ester, right? So simply I have done the esterification, I get back my benzocaine. So like this, retero and real, both you should balance. Retrosynthesis and real synthesis, both you should balance. While doing the retero only individually for every step, while doing the retero you should imagine the real reaction, whether it is possible or not. If the real reaction is correct, then only your retero reaction is correct. If real reaction is not possible, even on paper you have disconnected, you end up with a very good synthetic equivalent, even your disconnection is said to be wrong, right? So if you want to make a proper disconnection, while doing the disconnection only, you imagine the right reaction, imagine the real reaction, whether this reaction is exist or not, whether this reaction is possible or not. So by using that possibilities only we will see, right? If you see in another example, we have a para-methoxyacetophenone. So in para-methoxyacetophenone we have a methoxy group and acetyl group. Simply which group you will disconnect? Donating and withdrawing. So simply disconnect the electron withdrawing group, you will get the OMe, and after that what do you do? OMe, do the FGI, you will get the OH, alcohol ethers will changes into phenol. right? So if you see the real reaction, OH is there, simply do the protection. If you do the protection, you will get the anisole you will get. After that, do the acetyl chloride in presence of AlCl3. Here important aspect is why we are protecting the CH3. If you are not protect the CH3, what will happen? The reaction will not takes place. Why? Because in phenol there are lone pair of electrons are there. In AlCl3, instead of first step, if you do the direct second step, AlCl3 have a empty orbitals. So oxygen have a lone pair of electrons. These lone pair of electrons and AlCl3 both will react and adduct will form. So in order to overcome this problem, what we are doing? First we are protecting our OH. Protecting, or it is also called masking. Right, we are masking the OH from the CH3COCl, like we are hiding the OH, right? So first step is hiding the OH, that is masking or protection. After that, do the acetylation by using AlCl3. This reaction is also called Friedel-Crafts acylation, right? You will get back your product. So this is one. So in guidelines already we have discussed. So if you see the examples, in example 1, what we have, acetyl group is there, isopropyl group is there. Which one you should disconnect first? You should disconnect acetyl but not isopropyl. So A and B, which is correct? Which is correct? A is correct. Why? Because if you disconnect first alkyl group, what will happen? Acetyl group is left on the benzene ring. Acetyl group is electron withdrawing group. It acts as a meta director, right? So how the alkyl group again it will attack? It is not possible. So you should not disconnect the electron donating group first. So disconnect the electron withdrawing group. You left with a cumene, that is isopropyl benzene. Now isopropyl benzene upon Friedel-Crafts acylation, what will happen? Isopropyl benzene acts as a orthone para director, but what will happen? Isopropyl is a very bulky. Actually it should end up with the two products, but what happened here? Isopropyl is very bulky. So because of that, due to steric hindrance, ortho product is very less. It is a stereoselective reaction. The ortho product is very minor quantities it will form. We will end up with a para cumene, which is our precursors, right? Now here a very big complex, but don't worry. So if it is complex, it will be more fun. So NO2 groups are there. NO2 is a strong electron withdrawing group. Methyl group is activating group. OCH3 is a plus M group, that is activating. Alkyl groups are plus I groups. So these are also activating. So which one you should disconnect first? As we discussed, first strong electron withdrawing group. After that moderate electron withdrawing group. After that weak activating group. After that strong activating group. This order you should remember, right? So which is a strong electron withdrawing group in this? NO2, right? So first step you should disconnect the NO2s. After that weak electron donating group. So three are electron donating groups. One is methyl, OCH3 and tertiary butyl. So OCH3 is strong activating, CH3 is also strong activating, tertiary butyl is weak activating. So disconnect the tertiary butyl, and after that OCH3 and CH3 do the FGI, you will get the phenols, right? So the forward reaction also given, you can go through it. So these all guidelines already we have discussed. So one important guideline which we have missed is guideline number 5. So if you see here, it is a big challenge. Why? Because benzene consists of methyl and chlorine. Methyl is ortho para director and chlorine is also ortho para director. If you disconnect the chlorine to the toluene, you cannot introduce a chlorine at the meta position. Why? Because it's ortho para director, you can introduce in a para. If you disconnect the methyl group, what will happen? You will get the para-methyl. In such cases, what we will do? We should use the dummy groups. We should introduce one dummy group which can be removed very easily. So what I will do during the transformation, first I will use the dummy group. As we discussed earlier, NH2 is a dummy group. I have introduced the NH2. After that I have removed the chlorine and I have done the FGI. NH2 is changes into NO2 and after that I have removed the NO2. If you see in original synthesis mechanism, toluene is there. Toluene upon nitration you will get the para-nitrotoluene, and tin HCl, acid medium metallic reduction. NO2, what will happen? It will changes into NH2, and acetic anhydride. Acetic anhydride is a acid where the base is there. NH2 is a base, so acid base reaction will takes place. You will get the para-acetonylide, and after that Cl2 chlorination. So in chlorination, what will happen? Para already blocked, so because of that ortho position chlorine will be attacked, and HCl water, if you do the acid hydrolysis, the acetyl group will be deprotected, right? So you will get this product, and after that do the diazotization and H3PO2. NH2 will changes into diazonium salt. If you will use the H3PO2, it will replace with the hydrogen and you will get the metachloromethyl. So it will look very small but very important. Whenever you will get this type of problems, you should introduce the dummy groups, right? So by this way, by using these guidelines, we can synthesize, we can do the disconnection of any molecule in the universe, right?
Okay.
Thank you.
Okay, next Mohanbabu garu. Please explain the different strategies in retrosynthetic analysis. Please explain very briefly.
Yeah. So in the retrosynthetic analysis, so we will go with the different strategies here, right? So generally here in the retrosynthetic analysis, just we will disconnect the appropriate bond here, right? So as Areef sir told, right, the guidelines, 5 guidelines are very important here. So as per that guidelines, you need to disconnect a appropriate bond, right? So it should not be the random manner, it should be meaningful here, right? By disconnecting that particular appropriate bond, you will get the forward reaction. Otherwise the reaction will not be takes place here, and you won't get that particular target molecule here, right? So for that, so we will follow a very strategic planning here, right? So we'll generally we have 4 strategies are involved in this particular disconnection approach. One is a transform based strategy, and structure based strategy, and retron based topological based strategy, and stereochemical based strategy, and functional group oriented strategies here. These are the very important strategies which are applied in the synthetic strategies here, right? So we will see the examples for each and every strategies here. So transform based strategies, right? So in this particular strategy, so what you do is just we will convert this particular target molecule, right, into the different precursors here, and which is the reaction easily feasible when you are doing the forward reaction here. Okay. So in this particular example, you can see where this 1,5 diketone compound, where it is undergoing the Michael transformation, and we are getting the 2 precursors. One is the acetophenone and the alpha beta unsaturated ketone here, right? So when you do the Michael addition reaction, again you will get that particular 1,5 diketone compound here, right? And in the second example, you can see tetrahydrocarbazole here, carbazole compound is there, right? So when you apply the Fischer-Indol synthesis, you can get that particular carbazole product here, and for this particular transformation, you can take the phenylhydrazine, methyl phenylhydrazine, and cyclohexanone as the precursor compounds here, right? So means just you imagine that the reaction whether it is takes place or not, right? And what are the simpler precursors which used to get that particular target molecule here, right? So that means that criteria should be you keep in your mind, and the reagent must be appropriate to that particular reaction here, right? So that is transform based strategies. And next type is a structure based strategy, right? So in the structure based strategy, you can see this involves to identify a very potential structure which is feasible to get the particular target molecule here, right? So when you do the disconnection of this particular the giant structure, which is having the different types of bonds here, you can see the carbon-carbon bonds and carbon-nitrogen bonds here, right? So as the guidelines which are just now discussed here, right? So first you disconnect the bond which is which is attached to the heteroatom here, right? So in that way you can disconnect this particular bonds as per that guidelines, and you will get the different strategy, means different synthons here, right? Again by combining all these synthons here, again you will get that get back your starting material here, that is a target molecule, right? So that is means here that involves to identify a potential starting material, right? Next going to the topological strategies here. So this topological strategies, it involves generally it is taken for the molecules which are in the cyclic compounds here, right? So when the molecules are in the spiro structure or the fused ring structure or bridged ring structure, so in that case very carefully you disconnect the particular bond here, right? So in this particular tricyclic compound, just the bond which is not common for the both rings should not be break down here. So the bond which is not common for that the rings, it should be break down, and you will get the different precursors here, and by taking the precursor you can build up the your target molecule here, right? And the next type of strategies is functional group type of strategies here. Yeah, stereochemical strategies here, right? So when the molecule is having, when the target molecule is having the stereogenic center, then it acquires a very complexity to particular target molecule here, right? So to avoid that problem, you need to design a synthesis where the precursor must not have any stereogenic center, right? So in this way, you can see this particular compound, it is having the stereogenic center, and we are break down that particular bond in order to get the minimal stereogenic centers are present in the precursor molecule here, right? So this is the next type of strategy is functional group based strategy here. So in this particular strategy, so what you do is just we will do the addition of the functional groups and removal of the functional group to simplify the reaction pathway here, right? So what we are trying to do here is we are simplifying the reaction pathway by doing the different operations like functional group addition, functional group removal, or what is it, by doing the breakdown of that particular bond here, right? So you can see in this particular example where it is having the amino group and ester groups are there, right? So when you do the disconnection of particular compound, right, so we will do the transform into the acid group where the ester group is going to cleave, and we are converting it into the acid group, and further where the amino group is converting into nitro group here, where we are doing the oxidation here, and further we are doing the decarboxylation where we are getting the nitrotoluene here, and by doing the disconnection of the nitro group where finally we are getting the simpler structure, that is a toluene compound here, right? So in this way we are going to follow different types of strategies in order to build up a very feasible reaction pathway here.
Okay, sir. Okay. Then in this entire program, we are discussed about the definition of the synthetic strategies and the disconnection approach, retrosynthesis analysis, and various terms involved in the synthetic strategies. And also we are also discussed about the well explained by the Areef sir, synthesis of aromatic compounds by the various synthetic strategies, and also Mohan sir explained various terms involved in the synthetic strategies, and also various strategies for the retrosynthesis analysis. Then very thank you sir for explaining our student about this topic. Okay, thank you very much for this.